This is section 2.8 on solving equations that contain exponential or logarithm functions. We'll be taking a look at both of them, but the one thing you need to keep in mind, no matter which way we're going, is to remember that a common method for solving equations is to apply inverses in order to undo whatever's been done to x. We're going to see this over and over in this section. It's going to be important to keep in mind that we know exponential and log functions are inverses of one another. All right, we're going to start by solving logarithmic equations, equations that have a logarithm in them. Here's sort of a step-by-step outline of how we're going to deal with this, but hopefully it'll make sense as we go through. We'd like to start by isolating the logarithm. And when I say isolate, I mean get it by itself. If there's anything added or subtracted or multiplied by it, we always want to go ahead and do the opposite to get that stuff on the other side. So get the logarithm by itself first. Here's the inverse. We'll then apply the exponential function that is the inverse of the log, which should have the effect of kind of canceling out the logarithm. They're inverse functions, they do and undo. At that point, we should simply be able to solve for x. No matter what we're doing, of course, we always want to make sure we're doing the same thing on both sides of our equation. So let's start here in example 1. The logarithm base 5 of x equals 3. This logarithm is already by itself. Nothing is being added or multiplied or anything to that log. So I'm going to say, well, let's see, this is a base 5. So I'm going to use a base of 5, and I'm going to raise both sides on a base of 5. Notice I've done the same thing on both sides, but because I've chosen the inverse function, exponential and logarithms are inverses. That's the composition of inverses. They do and undo. I just end up with x over here. So x is equal to 5 to the third. Just a comment. When you look at the statement, when we first were learning about these inverse functions, exponential and logarithmic, we were really looking at both of these forms. And so if you feel comfortable simply changing the logarithm form to the exponential form without writing out that step, you certainly can do that. 5 to that third power equals x. All right, in this case, there's nothing left to do except say 5 to the third is 125, and we're done. We've solved for x. Let's look at number 2. Here, our logarithm function is definitely not isolated. The logarithm function consists of the log base 3 of the argument x squared. So I want to get that by itself. In order to do that, I'll have to add the 5, first of all. And then I also need to divide by the 4. All right, now my logarithm is isolated. And so I'm going to choose to say, let's go ahead and exponentiate. I'm going to put a base of 3 on both sides. Here are my inverse functions. And so I just end up with the x squared equals 3 to the fourth, which is 81. To solve, I'll just take the square root on both sides, keeping in mind I need to make sure I allow for both the positive and the negative. And x is plus or minus 9. We do always want to be careful when we get the negative answer to a logarithm problem. We know we can't take the log of a negative number. So when I go back and plug in, I'm going to notice that that negative 9 would have been squared before I took the log. So it was okay. That would be the log of 81. Sometimes negative answers have to, or anything that results in a negative argument in a log has to be thrown out. And we always want to check our answers to make sure before we decide that we're good with them. Let's look at a few more. In number 3, my logarithm is already isolated, so I'm good with that. But what's the base on this one? If you remember, this common logarithm really has a base of 10. So to get rid of a log base 10, I'm going to put in a base of 10 and raise both sides to that power. The exponential and the log are inverses, so the left side is just 6x minus 2. And the right-hand side, 10 to the first power is 10, which, of course, is a nice simple little equation to solve. 6x equals 12, so x equals 2. Just double-checking. Plugging in the 2 there, I'd be taking the log of 12 minus 2, the log of 10. Positive argument is fine, so we're good to go. Watch out for these situations. In number 3, the whole 6x minus 2 was in the argument, so I could go right ahead and get rid of the log with the exponential base 10 immediately. In number 4, that minus 2 is not part of the argument. It's outside the log. So I need to isolate my log by adding the 2 first. The logarithm of 6x equals 4. Okay. Notice I cannot remove something from the argument. I was not able to add the 2 on this one because it was inside the log function. It was part of the argument. I can only multiply, divide, add, subtract things that are outside the argument of the log function. Now that my log is isolated, once again I'm going to exponentiate on a base of 10, both sides, and use that inverse property of the exponential and the log to say that the left side is just 6x, and the right side, 10 to the 4th power, is 10,000. Dividing by 6, that's not going to come out evenly. If I reduced it by dividing top and bottom by 2, I think that's the best I could do for an exact answer. Of course, you could grab your calculator and get a decimal approximation if you wanted to. 6 times a positive number is still positive, so I am taking the log of a positive value, and I'm good to go with that. In number 3, once again, I need to isolate. I'm just going to remind myself, the log base b of 45 is the logarithm piece. I need to get that by itself before I can do anything else. So I'm going to add the 1 to both sides. And then divide by the 3. All right, this time, my logarithm has an unknown base, but it doesn't change how I do things. I still want to get rid of that log base b, so I'm going to apply the inverse function. I'm going to exponentiate both sides on a base of b. Inverses get rid of each other, and the left-hand side just becomes 45. Equals b cubed. To solve for b, I can take the cubed root, or sometimes we like to think of it as the 1/3 power on both sides, And we know that multiplying those exponents is just going to give us b to the first, or plain old b. And our base is approximately 3.557. Let's call that. It's an approximation, though. Bases have to be positive, and it did turn out positive, so I'm okay. All right, one more example of these. Let's see. My logarithm is all of this. All of that x squared minus 6x is inside the argument. So I can't move any of that. That's got to all stay together. The only thing I can do here is subtract the 5. Now that the logarithm is isolated, I'd like to get rid of that logarithm. It's a base 2, so I'll exponentiate both sides on a base of 2, allowing the inverse functions to act on one another, and giving me just x squared minus 6x equals 2 to the 4th power, or 16. See, I got a little quadratic equation here, so I'm going to get it equal to 0. And I'll try to factor. If it doesn't work, I can always use the quadratic formula if I have to. But I'm thinking a sum of negative 6, product of negative 16. That looks pretty good. Negative 8 and positive 2. So x squared has to be x times x minus 8 and plus 2. That's going to give me x equals 8. And that one's going to give me x equals negative 2. Again, I want to make sure that in both cases I'm not trying to take the log of a negative number. If I were, I'd have to throw that away. So I'm just going to double check real quick. Inside the logarithm here, x squared minus 6x, if I do 8 squared minus 6 times 8, that's positive. That's okay. I can take the log of a positive number. Let's also double check the negative 2. Negative 2 squared minus 6 times negative 2. That's also 16, also positive. So those are both legitimate answers. Had either one of them made what's inside the log negative, I would have had to throw it away as a possible solution. All right, so there's a few examples of solving equations containing logarithms. In the next video, we'll take a look at solving equations that contain exponential functions.